All right, this is video 1 on exponents and logarithms. Actually, I won't mention logarithms at all on this one, so it's video number 1 on exponents and logarithms, but it's the video just on exponents, or the exponential function. All right, so this has been a seed that I planted quite some time ago, very first day of the class maybe, where I mentioned Henschel's 5 levels of understanding a function. And you know, when I put my name on something, it just means it's not really much of a thing. You can't Google 5 levels of understanding a function and get anything out of that. It's just, I think, a good way to describe something. And this is one of those moments when this thing that I brought up, it just seems like it has to be 5. Even the author goes to, I don't know, almost comical extremes to make sure he hits all 5 of these points when the author introduces the exponential function. So what am I talking about when I talk about the exponential function? I'm talking about a function of the form f of x equals a to the x. A just has to be a positive number and not 1, but it doesn't have to be 2. It could be any base that is positive and not 1, and it would still fit the family of exponential functions. So let's go through this problem, this one numerically. So that's, of course, level 1. So I think you'd all understand that, not just understand, but even anticipate that this was coming. By the way, I just kind of pushed everything too far up there. Okay, so this is the function, f of x equals 2 to the x. So if I put in a 3, it's 2 to the 3. And we all know what to do there. In other words, this has been a seed that's been planted in your head, I don't know, years ago, by somebody other than me who taught you that 2 to the 3 means 2 times 2 times 2 equals 8. All right, that's not a good sign. All right. Well, there is it's a little more advanced, maybe years after you learn about 2 to the 3 equaling 8. It's also true that 2 to the, let's do these one at a time, 2 to the negative 2 has a numerical answer that you can figure out, or you should be able to figure out. Anyhow, what does a negative exponent do? Negative exponent means 1 over that. So 1 over 2 to the x, or 1 over 2 squared, and that equals 4. Sorry, a little distracted because I'm plugging in my tablet after that low power warning. Okay. 2 to the 0 equals 1, a numerical fact that we learned at some point. 2 to the 1/2 means the same thing as square root of 2. I'm just going to leave it as square root of 2, although we could run it through a calculator and find its decimal, but you get the idea. By the way, this is going to come up later. Notice that this function has no trouble with negative numbers in the x-axis, in the argument. 0, obviously positive numbers are fine, because that's what's the next question. Next question is, what's the domain and range? So what we have to do is we have to think of the domain as the set of all x values that will not give an error on a calculator. I put it that way intentionally, so you understand what we're talking about. We're just talking about the x values that wouldn't give me an error. So I could put in a negative number, I could put in a positive number. You probably get the idea. All right, we're going to write that down in a minute here, or reveal that answer in a minute. But okay, what's the range? Well, the range is a set of all possible y values on a calculator. So, could you get, I don't know, 10, or could you get some number? Well, we're going to say that we could get any number, but only if it's positive. And that's kind of interesting. Let's look what happens. When you put in a negative number, you see how the answer is not negative. You put in a negative number, the answer is a fraction. So you can think about this a little bit. And you would find that for this function, the range is 0, infinity, and the domain is negative infinity, infinity. Again, I'm using interval notation where I put the minimum comma the maximum. All right, underneath this, I decided I'd write, maybe you remember the domain for square root of x, the domain and range. The domain and range there were 0 to infinity and 0 to infinity. So, I don't know, we've seen something kind of like this before, but not exactly like this before. Notice how square root function contains 0. You can get 0 for the answer, but not for this one. So this is a new function with a domain and range in that pair that we haven't seen before. All right, this might look a little funny, but what is next is the graph. So I say the graph and the shape. So the graph includes knowing the shape. That's what's written underneath there. Knowing the graph requires us to know the shape of, and I lost the whole graph. That's fine. I'll rewrite it. And how does this work? All right. Well, you shouldn't be trying to graph a function if you don't know it numerically. So what I have on this table is some numerical calculations for the function y equals 2 to the x. So I want you to look above that below that red line first. If I put in 0, we already know this. If I put in 0, 2 to the 0 is 1, 2 to the 1 is 2. So in other words, I'm picking my x values, calculating each of these y values. And I even did that for negative numbers. If I put in a negative 1, well, I know that's 2 to the minus 1, which we calculated earlier is 1/2. So I had those. You've seen those just a moment ago. All right. And then what I did was I went ahead and gave these a letter, just so you can see what point I'm talking about. So here's point A, point B, point C, and I lost it, but point D is way up here. Point D, 3, 8. All right. So, but there's more to it. Obviously, these negative numbers that I'm giving it a different, part of the alphabet too. Well, here's the pattern you want to notice. Notice how high point A is. Well, it's 1. If I take a step over, one step this way, how high is point B? Well, it's 2, but what I want you to see is it's twice as high. So it's twice as high. If I take another step over, it's twice as high as the previous one. So this one was 2, this one's 4. I take another step over, still twice as high. So all of the points just keep on, doubling in height. And that is how exponential graphs work. If I go the other direction, it's half as high. So half as high, half as high. So it cuts in half as I go in this direction, and it doubles as I go in this direction. By the way, exponential graphs like this have been getting a lot of press lately because of the COVID-19. So you might see a graph that looks something like this, that a curve they're trying to flatten. Right, was what they're talking about. All right, so that's it. That's our new shape. You might have seen it when I was running through this before. I said, I like to think of this as a slide, a water slide. It's kind of the shape it reminds me of. Water slides are sometimes really steep and they level out. They level out at ground level. They don't go below the ground. Yeah. So it looks like a water slide, one of those really steep ones. All right. Graphing. manipulate. Oh, I gotta erase all this. Okay. So manipulating a graph is a little unusual, I suppose, because it's not simplifying, because we don't really have any rules for simplifying exponential functions. We have rules of simplifying everything. We have rules for simplifying radicals, but we really don't have rules for simplifying everything. So these functions are fine. They're not wrong. It's just that I can manipulate them. So what am I going to do to this one? Well, you might have seen it. Oh, I'll erase it. So I'll go in some other color, and I want to think of this function, that 4, as 2 squared. Again, I'm not saying this is unnecessary rewriting or manipulation, but it's a possible manipulation. So in other words, at the end of this, I just want you to agree with me, like, okay, that's true. All right. And then now here, these two can multiply, so that's 2 to the 2x, and that's it. That's my manipulation. So what I'm saying is 4 to the x is the same as 2 to the 2x. I'm not saying one's simplified and one's not simplified. I'm just saying they're the same. If I were to put a number in here like 2, 4 squared would be the same as 2 to the 2 times 2, or 2 to the 4. And it's true. They'd both be equal to 16. But more than that, they'd have the same graph, they have the same domain, they have the same range. They are the same function. I can manipulate it. All right, now, on this one, we could all manipulate 2 to the minus x as 1 over 2 to the x, but that's not going to take me anywhere. In other words, that's not really what I'm trying to do here. I want to manipulate it into another exponential function, and exponential functions are, wait for it, a to the x, all right? Not 1 over something. So there's got to be an a, got to be an x. All right. And I guess this maybe kind of doesn't qualify as being a purely exponential function because I'm messing with the x here with a minus sign. But that's not what I'm trying to say. I'm just trying to say that we can write this some other way. And actually, I guess I can say that. We can write this more like a to the x, not something to the minus x. My a would have to change, but how? All right. So here's the manipulation I'm going to use. Skip the step. All right. I'm going to think of this as -1 times x. Just put them together or separate them. Minus x can always be thought of as -1 times x. Just kind of making the one, that's supposed to be that one. Okay. You see it. Let me try it one more time. -1 times x. And I didn't need that parenthesis. Goes along a lot of steps to get to that point. All right. So I have that. And why is that interesting? Well, what that means is, let's go down here, I can think of that as 2 to the -1 raised to the x. In other words, that same rule I used here, but this direction. If I have a multiplication, I can write them each separately. And so I can further think of that as 1/2 to the x. That's it. I can change 2 to the minus x into 1/2 to the x. I guess maybe one of these is a little more simplified, we just don't use that word, than the other. But it's just equal. That's really all we're trying to say. They're equal. for all purposes. The graphs are the same, the domain's the same, the range is the same, everything's the same if I have 2 to the minus x or 1/2 to the x. So, might be interesting. All right, and now this might be the strangest part of all, and it's not that there's anything too strange about my outline. It's just that every book seems to want to talk about this. Again, what I find strange about this is most people have never heard Henschel's 5 levels of understanding a function, and certainly the author hasn't. But the author still has us solve for x. Remember the whole thing. Cancel, solve for x, or free the argument. All right, so that's what we're going to do. We're going to solve for x. I say sort of because we're not anywhere near being able to do this for real. The author just wants to give us this glimpse of this process, maybe. I don't know. But again, why does the author want to do that? Is he following my outline? I don't know. But so don't worry about that. Here's how the author is going to do it. All right. This particular problem can be rewritten as 2. I'm not going to rewrite anything, change anything here yet. To the x, and then 32 can be written as 2 to the 5. All right, and I'm just going to say that's great when you can get it. That's great when you can make that happen. But honestly, you can't always make this happen. So that's why I say we're not really covering this whole thing. In other words, if that were a 30 instead of a 32, I couldn't do this. And if this were something other than a 2, if it were a 3, it wouldn't help to get a 3 on this side and a 2 on that side. So these numbers had to be hand-picked for this idea. And what's the idea? The idea is if you have a to the, what letter, u equals a to the v, I can cancel the a's and u will equal v. This is a very temporary rule that we're just using for now. And I'll explain how unusual that is in the world of mathematics to use this rule in something you'd understand. Our go-to function for most functions is square root. We all understand square root. But basically, some mysterious force cancels these 2's, and I get x plus 1 equals 5, or x equals 4. And this is correct, meaning I could check it. 2 to the 4 equals, 2 to the 4 plus 1 is 32. And that's true. 2 to the 5 is 32. So in other words, we could get this, but we're going about it as at a fairly unusual way, this idea of canceling a function. So here's what it reminds me of. Let's say I trained you to solve the square root of x plus 1 equals 3, not by squaring both sides, but instead by changing that 3 to the square root of 9. Of course, it's true that 3 is square root of 9. And then I further said, if you have just one perfect square on one side and one perfect square on the other side with nothing else, you can't have multiplications on the outside or anything, you can just cancel those square roots and you'll get the right answer. Well, as accurate as that is numerically, I mean, it's true, it's obviously hiding the fact that we had another way of doing this. In other words, I could have just squared both sides. And the square would cancel this, and the square would make that 3 into a 9. Turns out we have a function called logarithms that will make what we did here feel a little bit obsolete. But the author brings it up right away in the first section, so we might as well talk about it here as well. All right, so that is our first idea of exponents and logarithms, solely talking about exponents. We'll have more videos to come on this topic, but that's exponents.